Hi everyone, welcome to my channel. So in this particular video, we are going to see about our next activation function, which is Relu Activation Function. So we have already discussed about sigmoid and tanh. So in those particular activation function, actually we faced vanishing gradient problem as well. So let's discuss about Relu Activation Function and how it resolves that vanishing gradient problem, as well as let's see some of the functionalities, advantages and issues of Relu activation functions. So yes, Relu is nothing but the rectified linear unit. It is a linear, you can say it is a linear activation function which transforms, like any input goes to the Relu activation function, it transforms through a linear linear functions, right? So as you can see in the particular graph, so this function, this Relu activation function is very much simple. So what it means, for any negative or zero values, if the input goes to Relu is negative or zero, so the output would be zero, or any positive, for any positive input values, the Relu function will give you that positive value. Whatever positive number you pass into the Relu activation function, it gives you that positive number. So as a Python, you can write the max function. So supposedly this is the actual formula, or you can say this is the actual function of Relu activation. So maximum of zero or the positive number. Okay, max of zero and positive number. So it ranges from zero to infinite. So it ranges from zero to positive infinite, because whatever positive number you will provide, it will give you that positive number. Okay, so yes, this is the transformation of Relu activation function. But in the backward propagation, when we try to calculate the derivatives, so the derivative of Relu activation function, it will give you zero for any negative values, or zero values as well, or one for any positive value. So if your input is positive, so in the backward propagation, so the derivative would be plus one. Okay, so let's see what are the advantages. So we'll have some differentiation over overcome to vanishing gradient problem. So as we have already seen in the sigmoid activation function, while calculating the backward propagation, the derivative of sigmoid is 0.2, like it ranges from 0 to 0.25. So if you goes and calculate the derivative of sigmoid function for each layer, so the value will decrease if you increase the layer. So actually it results in the vanishing of gradient, so it comes to a zero. So that there would be a problem of doing the weight optimization or weight operation. Here actually in the backward propagation we are getting one value, so that so the vanishing gradient problem actually mostly disappears. And the second advantage, it's not activate all the neurons at the same point of time. So it kind of regularize, like you can say as a dropout is also a functionality used in neural network. So it regularizes. So what it means, so it doesn't take all the parameters. So the computational expensive actually quite resolves, because for any negative value, as you can see, for any negative value, actually it provides the output as zero, right? So if it gets if it gets zero, so the output goes to the next neuron is would be zero. So the neuron actually gets deactivated because the output is zero. So actually certain neurons get deactivated. Um so it actually simplify, like it helps to simplify the model. So yes, this is one particular advantage of Relu. And computationally simple, as you can see, this is very simple formula. Like for negative value it will just provide zero, for positive value it will just provide that positive value. So there is not too much headache in calculating the exponential or any type of exponential or any complex calculation. It is quite simple. And the last advantage, as you can see, cause of linearity, it is easy to optimize, because as you can see, it just provide the linear graph. So it is very much easy to calculate the gradient or slope, you can say. So yes, the optimization of gradient is quite easy for linear. Okay, so but the most dangerous, or you can say the most difficult issues that we are going to face is dead neuron. Dead neuron is nothing but that when we do the backward propagation, I have not shown you guys the entire neural architecture. So as you can see, so supposedly I have taken three layers. So during the backward propagation, calculating the derivative of three layers, which contains Relu activation functions. As you can see, so oppositely I'm getting because Relu activation function will provide two values. There is not range. You just provide one for any positive or zero for any negative. So supposedly one value actually we get zero. So if you multiply uh, this zero in the backward propagation, the entire gradient becomes zero. So it could be result in the dead neuron, because there won't be any weight optimization, like there won't be any weight optimization, because the entire calculation during the backward propagation goes to zero, as the formula suggests in the derivative of ReLU. So this is the problem. So let's see how we are going to overcome this problem in the next activation function. So this is all about ReLU activation function. So thanks for listening, guys. If you have any doubt, try to comment me out. I'll try to solve all of your queries. Thank you.